So, good morning, everybody. Welcome to this IMS Medallion Lecture session. I'm chairing, I'm Ian Johnston, and I commend you all for coming this early on this Thursday morning. So perhaps you already know and appreciate Boaz Nadler, as I do. So Boaz and I have been friends and collaborators for many years, and I'm always in love with his enthusiasm, his warmth, his originality. It's wonderful. Biographically, Boaz has all his degrees from Tel Aviv University, and then he began as junior faculty at Yale. And in 2005, he joined the Weizmann Institute in Israel, where he continues now as the William Petchek Professorial Chair in Mathematics. He has very broad research interests across all of mathematical statistics, statistical machine learning, and more generally applied and computational mathematics. He's also interested in statistical applications in signal processing and computational biology. In 2018, he was awarded the Abarbanel Prize in Applied Mathematics, perhaps the inaugural one. Yeah. That's from the Israel Mathematical Union. And in 2023, he was named a Fellow of IMS. And of course, today, he's one of the 8 IMS Medallion Lecturers that's selected by a competitive process each year across all of the topics and areas that IMS covers. So, the medallion symbolizes this honor, and so I'm presenting it to Boaz on behalf of IMS and inviting him to present a lecture on finding structure in high-dimensional data. So let's go on.
Yeah. Okay, good morning, everyone. I hope everyone can hear me. So I also commend you for coming this early on the very last date of this wonderful conference. And thank you, Ian, for your very kind words. And I will talk today about a journey, several works that I've been doing over 20 years since I first stepped into research in mathematical statistics. The second part of the talk will be about the most recent talk. I'll show you some interesting phenomena in high dimensions in semi-supervised learning of a mixture of Gaussians. But as you will see, we had to climb these 20 years of work, not only of myself, but of many others, to reach there. So we will combine several works to get to a new height, if you wish. And before I start, I'd like to thank all my wonderful students, postdocs, collaborators over the years, and many, many others, colleagues that have helped me navigate the research world. And of particular relevance to this talk, I'd like to thank Peter Bickel, who's here, Ian Johnston, Debashish Paul, Robert Krautkammer and Dan Vilenchik, with which I did some work on sparse PCA, and 3 students of mine, Aaron Birnbaum, who unfortunately died several years ago, Gil Kuh, and Eyar Azar. Okay. So, and this talk will be introductory. It's early in the morning. We'll take it slow. So, broadly speaking, when you look at data and tasks, you can, categorize them into 3 distinct types at a very high level. One is supervised. That's perhaps the thing that's most standard in machine learning. You observe data x, y. Y is your response. X is your explanatory variable, and your goal is to predict y for new x's. And if y is binary, it's binary classification. If y is continuous, it's regression. There are many methods, lots of theory, so I will not talk about this in this talk. What I've been doing for many, many years is more unsupervised learning, exploratory data analysis. Here we only observe x's, we believe that these data has some latent structure that we would like to uncover. And in some cases, there was a response Y, but unfortunately, we don't get to see it. And the goal is to somehow find the structure hidden in X, and we'll see some examples of this in my talk. So that's one setting that we will look at. And the setting that I will look at also today is called semi-supervised, and here we observe two types of data sets. One is a labeled data set, so samples X, Y, L of them. And in addition, we observe an additional subset of samples of only X's, okay? So few labeled samples, possibly lots of unlabeled ones. There are many applications where labeling is expensive, but just collecting data is much easier. And the underlying idea is that maybe somehow this unlabeled data that perhaps has some interesting structure that we want to uncover will help us to construct a more accurate classifier. And a key question is, when does unlabeled data help? How should we use it, etc.? So I think this field, although there have been several works in this area, I'm not going to cite all of them here, but I think it's still not sufficiently explored. It has very many practical applications, many heuristic algorithms that seem to work, but I think that there is room for more theory. I'll show you a snippet of some theory or some interesting observation in a particular case today. Okay, so broadly, what I've been working for the past 20 years is trying to understand some theoretical foundations for both unsupervised and semi-supervised learning. And there are a host of questions that myself and many others in the community have asked. First, on the modeling aspect, what types of structures or models are useful? On the algorithmic side, both develop methods, but also try to analyze them. How will they perform? And of course, we want our methods to have practical polynomial time. And on the theoretical side, you can also ask, well, what are fundamental limitations? When are there structures that you're not going to be able to detect even if you had a supercomputer? Okay? Okay, so the outline is, again, the focus is on a high-dimensional setting. The number of features is going to be very, very large. Dimension P, either comparable to sample size or maybe much larger. I'll present some mathematical, statistical, computational problems, few partial answers, several open questions. Okay, let's start. And the running example I'll use in this talk is a classical one, trying to learn a mixture of two Gaussians. So even a balanced mixture. So there's a response Y, binary. You just flip a coin, +1, -1 with equal probabilities. And then conditional on Y, X is Gaussian with a mean mu1 or a mean -1 and identity covariance. Okay, so one of the simplest possible models. So mu plus and mu minus are the centers. Delta mu is the vector that separates the two Gaussians. Throughout the talk, I'll use lambda as the measure of separation. You'll see in a minute where this factor of 1/4 came from. So here's a simple example in 2 dimensions, data from two Gaussians. Here are their centers and the vector delta mu separating them. Perfect. So if we observe data that came from two Gaussians, in a supervised setting, we would like to construct an accurate predictor for the label Y for a new X. And in unsupervised setting, of course, you would like to cluster the data into the two Gaussians. But let's first focus on the supervised case. The optimal classifier under 0, 1 loss is linear, right? It's the hyperplane orthogonal to delta y. And the base optimal error, I won't write the formula. The key point is that it's exponentially small in the separation. So large separation, very small error. Okay, perfect. I'll go to 100 years ago or more. The standard method to do it is linear discriminant analysis. You just plug in estimates of mu plus and mu minus from your label data. We know that if dimension p were fixed, sample size went to infinity, this is a consistent estimator. You would get to the base error. And here's an example. Here dimension is 50,000. Separation parameter lambda is 4. And you can ignore k for now. But what you can see here, the x-axis is the number of labeled points. The y-axis is your classification error. The if you can see, this horizontal line is the base error. And if you get more and more and more and more data, then you converge to the base error. But you see that you can also prove it theoretically that to get sufficiently close to the base error, the number of label samples that you need scales linearly with the dimension and inversely with the separation. Okay, so if p is 50,000, you need order of 50,000 samples to get close to the base error. And in many cases, we don't get 50,000 labeled samples, but that's life. Okay. What happens in the unsupervised case? Well, you could try maximum likelihood. It's generally challenging, non-convex. There are many other methods to learn a mixture of two Gaussians or a general mixture of k Gaussians. One of them is EM. In this talk, I'll focus on a spectral approach, which for a mixture of two Gaussians is very simple. The mean of x, we only get unlabeled data, so we can just compute their mean. It's the average of the two unknown mu plus and mu minus. And the covariance matrix, if you do the computation, you see that it has a very simple structure. It's the identity, which is the covariance of the two Gaussians, and it's perturbed or added. There is an additional term, which is rank 1, which is delta mu transpose. So this is known as a spike model that was coined by Ian Johnston some 20-something years ago. And so spectral learning a mixture of two Gaussians is actually quite straightforward. You can compute the first two moments, the mean and the covariance. And from the covariance, you can extract the leading eigenvector, which is delta mu. So you have two equations in two unknowns, and you can get mu plus and mu minus up to a sign ambiguity, which if you don't know labels anyhow, you can switch the two clusters. Now, so this is on the population level. On the finite sample level, you can use plug-in estimates, so you can compute the mean by the empirical mean, compute the population covariance matrix, take its leading eigenvalue, an eigenvector, and hope it works. And again, if p is fixed, we know that sample size tends to infinity. We know that PCA is consistent. You will get consistent estimates of the centers of the two clusters. In terms of finite sample errors, so we know that the mean scales like squares p over n. And the error in the eigenvector, this is where things become more interesting and complicated. So again, if p were fixed and sample size went to infinity, you can show that the eigenvector error also scales like square root of p over n. But in high dimensions, this is where things start to become interesting, because there's a well-known phase transition where we look at an asymptotic limit as both p and n tend to infinity. The ratio tends to a constant gamma. And in 2005, Benarou, Baik, and Péchet proved the following result, that there is a phase transition for the eigenvalues. If the separation is sufficiently large, the largest eigenvalue pops out of the bulk. But if the separation or the signal strength is too small, you don't see an evidence of two clusters, let's say, or a signal from the leading eigenvalue. The leading eigenvalue tends to the edge of the what's known as the Marchenko-Pastur distribution. It tends to the value that you would get just from pure noise. Okay, and actually in statistical physics, people have heuristically found this formula a few years earlier, and they called it retarded learning because, like, it's retarded. It takes time till you're able to learn. Okay. 2 years later, or 3 years later, both Boaz Nadler and myself analyzed also the eigenvectors, which is what we're interested in here because we wanted to apply PCA, and we found a corresponding phase transition for the eigenvectors. Here I'm telling you what is the dot product between the true signal direction and what you find by PCA. And again, in the limit as Pn tend to infinity, if signal strength is too small, in our case, if the cluster separation is too small, asymptotically, the dot product is 0. You just find, due to fluctuations in the noise, a random direction where you had large variance due to the noise. If the signal separation is large enough, then there is some correlation between the eigenvector of PCA and what you find with PCA and the true signal direction. Okay. So, okay. So, in short, for weak signals, the largest eigenvector is uncorrelated to the true signal direction. Here is a simple illustration of this. The x-axis here is signal strength, lambda. The y-axis here is the largest eigenvalue. The blue line at the bottom is the true population eigenvalue. Here signal strength is, noise level sigma is 1. So when lambda equals 0, the eigenvalue is 1. It's not 0, the largest eigenvalue, but linearly increases with lambda. And what you see in red is the result of a simulation. Here dimension is 1024. And for a wide range of single values, the largest eigenvalue just remains unchanged. It's exactly at 1 plus square root p over n squared here. And the vertical line, the dashed vertical line, that's exactly the location of the phase transition from which you start to see evidence that there is a signal here. This is for the eigenvalue. For the eigenvector, here you see a similar phenomena. Because dimension p is 1024, if you just take two random vectors in dimension 1024, they would have a dot product of 1 over square root of n, so this is 1 over square root of p. So this is the value you see for lambda very close to 0, right? Square root of 1024 is roughly it's 32, so 1 over 30, that's what you see there. And only once lambda is larger than this vertical line, you start to see some overlap, significant overlap with the true direction. Okay. So what are the implications for learning a mixture of two Gaussians, at least by a spectral approach? So if you had two Gaussians, but they were not sufficiently separated, so their separation was smaller than the square root of p over n, then you wouldn't be able to learn the two Gaussians. You wouldn't be able to learn the clustering by a spectral method. Okay? Okay, fine, but maybe you could ask then, maybe you can still estimate this direction by some other method. Okay? We're not constrained to spectral methods necessarily. So this leads us to a different topic of projection pursuit, with which I've worked with Gil Kur and Peter Bickel. And let me give you a motivation in this context. Suppose we have data which is a mixture of two Gaussians. So if you project your data into the direction of separation between the two Gaussians, you'll get a mixture of two univariate Gaussians. And if delta mu is large enough, it will even be modal. You'll see something interesting. And in contrast, if you project the data into any other orthogonal direction, you had a mixture of two Gaussians, but you're projecting to an orthogonal direction, you just get noise. So the distribution will be normal 0, 1. So perhaps a way, I'm putting computational issues aside, perhaps a way to learn a mixture of two Gaussians is to search over many different possible projections for those that look non-Gaussian, or bimodal, or something along those lines, okay? So the question here is, if you have data that has interesting structure in some unknown direction, can you find it, okay? And of course, we didn't come up with this question. It was people who worked on it even before I was born. But the term projection pursuit was coined in a paper by Jerry Friedman and John Tukey in '74. And let me read. They proposed an algorithm for the analysis of multivariate data. Is presented, discussed in terms of specific examples, and the algorithm seeks to find one- or two-dimensional linear projections that are relatively highly revealing. And what does it mean, highly revealing? So in their paper, they propose a specific index for being non-Gaussian. And later on, many other authors proposed other methods based on cumulants, entropy, distance from a Gaussian distribution, etc. Now, the justification for a projection pursuit came 10 years later in papers by Peter Huber and Diagnosis and Friedman and others. This is David Friedman from Berkeley. And in particular, the paper by Diagnosis and Friedman, what they showed is that, so they said, well, let's assume that we have data and let's take a direction z. Let's compute the empirical distribution in that direction, a cumulative distribution. And what they proved is that if data is Gaussian, then all distributions will look Gaussian, okay? Not only a fixed one, but even if you do a supremum over all possible unit vectors on the p-dimensional sphere, all distributions will look Gaussian. This is if p over n tends to 0, okay? If sample size is much, much larger than the dimension. They also had a result in a high-dimensional case. Here is a statement of the result. They said if you have data that has no structure, all p coordinates are independent and finite moments, etc., then almost all projections are going to be Gaussian. Almost all with respect to the Lebesgue measure on the unit p-dimensional sphere. But almost all does not preclude that few of them will be non-Gaussian, okay? Let's keep that in mind. But this was a sound theoretical justification for projection pursuit. So if you search for a direction and you find non-Gaussianity, then it could not have come, it possibly could not have come from Gaussian data, and you found significant structure. Now, 30 years later or 50 years later, there were papers that proposed applying projection pursuit and modifications thereof to a fine structure in high-dimensional data. Here are just two examples of papers along those lines. And the question in the context of this talk is, can projection pursuit also work in a high-dimensional setting, okay? Specifically, can you still detect non-Gaussian structures if they're present, but if the dimension is very, very high? So that was the research question. Or in other terms, what are the statistical properties of projection pursuit in high dimensions? So this is a joint work with Peter Bickel and Gil Kur, published a few years ago. We analyzed the properties of projection pursuit in a high-dimensional setting as p and n tend to infinity, and the ratio tends to a constant. This constant can be also infinity, or it can also go to 0. And we asked ourselves, if you have no structure, which distributions can you still find in the data in high-dimensional settings? We identified 4 different regimes. One we call ultra-high dimensional, P over n tends to infinity. High dimensional where P over n tends to some constant gamma which is larger than 1. An over constraint limit where P over n tends to some gamma smaller than 1, and the classical limit. And we also looked at sparse projections. I'll not go over all the results. I'll just show you one snippet of those. I'll do some illustrating examples. So suppose you have a data scientist. He is given a P by N matrix, and he is given the task. We think there is some interesting structure in there. Can you find what's in this data? Okay, standard exploratory data analysis. Our data scientist, so first he just, as a sanity check, he just picks a random projection, and he had a data set with 400 samples, dimension 5,000, not very large. He makes a random projection. He makes a kernel density estimate, very close to Gaussian. Perfect, okay. Then he looks only at the first 2,500 variables. He had some prior knowledge of maybe even structure only there. And he searches for B-model distributions. He is able to find one. Here is a specific distribution our data scientist found, very far from the Gaussian distribution, right? The blue is a kernel density estimate, looks B-model, you know, every data scientist may be very happy to see something like this in data. So that was on the first 2,500 samples. He does the same exercise on the other P over 2 coordinates. He also finds B-model distributions, and he plots them on a 2D plot. So here's the projection of the data into direction Z1 that he found on the first 2,500, direction Z2 in the second 2,500. Looks like a mixture of two Gaussians to me. Okay, so he's very happy, very excited. He found the click separation of the data into two clusters. There is something I didn't tell you about this data, okay? And so, of course, we should always be skeptical. As statisticians, we should always ask, is this kosher? Is this statistically and or scientifically significant? And what I didn't tell you about this specific example is that, well, I generated the data, and I just generated the vectors being just normal zero identity, okay? So again, the P over n does not seem extremely large here, right? It's a factor of 12 or 12 and a half, okay? Not 100 or more. And I found this. And if you ask me for exponential distribution, I'll find you an exponential distribution. And if David asks me for a gamma, I'll also find you a gamma, if you wish. So high dimensions, you know, you need to handle things with extreme care. Because if you have high dimensional data, a limited number of samples, which we have in many cases, a very strong computer perhaps, and maybe a somewhat careless data scientist, you can find apparent structure if there is none. And you know, after we published our paper, other people, this is a paper in evolutionary embryology, and its title says, why clusters and other patterns can seem to be found in analysis of high-dimensional data. It's a paper that tells the community, their community, to be careful with how they do very high-dimensional data analysis. Okay, so let me give you a snippet of the theory that we developed in that paper. So we assumed data was multivariate Gaussian, so no structure at all. And this is the theorem that we have in the ultra-high dimensional case, when P over n tends to infinity. So when P over n tends to infinity, the theorem that we were able to prove is that it's a game. You choose whatever univariate distribution you wish, continuous, let's say, so it has a continuous CDFG. There will be a sequence of projections in the data. Remember, this is a sequence model as P and n tend to infinity. So there's going to be a sequence of projections that tend arbitrarily close to this G, which is non-Gaussian, B model, tree model, whatever you want, okay? So in short, if you give me enough high-dimensional data, I'll find you whatever structure you want to see, okay? All right. Now, if P over n tends to a constant, then we're more constrained. If this constant gamma is larger than 1, then any distribution that has a variance gamma minus 1 we can find in the data. If gamma is smaller than 1, then actually we'll never be able to find distributions that have variance larger than 1 plus square root of gamma squared. This is the variance in the direction of PCA. So any other projection has a smaller variance by definition, okay? There is a small gap here. We don't know what happens in the middle. Okay, perfect. So interim summary before I return to the mixture of two Gaussians. In the supervised case, everything is nice. Errors scale as square root of P over L. L is the number of labeled samples that I have. The problem is that if P is very large, I have a problem. In the unsupervised case, I need the separation to be very large for PCA to succeed, but the errors will scale as square root of P over n. And remember, n is much larger than L. Okay, and the question that I asked my student AR was, what happens if in a semi-supervised setting, okay? What happens if we have both a little bit of labeled data, a little bit, or maybe a lot of unlabeled data? Can we do better than by each of them alone, okay? And as we started to work on this, it was a few years ago, 2-3 years ago, there was a paper by Tifrea et al., and they studied the same problem, and they proved that, at least asymptotically, semi-supervised learning does not achieve a better rate over either supervised learning alone or unsupervised learning alone, okay? So if someone solved this specific problem, we had to change the problem a bit. And what we did was look at a case of sparsity. So as we all know, sparsity is a key concept in high-dimensional data. It what's allow us to be able to do something when we have a limited number of samples. And in our setting, what we assumed is that we have data from two clusters, two Gaussians, but only very few of all P features are informative, so only K of them, okay? So just to illustrate that sparsity can give you huge gains if it holds, I'm taking the same simulation I had before. So dimension is 50,000, separation parameter was 4. The horizontal line is the base error. This is what we got from LDA. Remember, we required number of samples to be proportional to the dimension to have close to base error. But now I'm telling you that we had only sparsity of 200. Only 200 out of all those 50,000 features were informative. And what I did here was something extremely stupid. I estimated the mean vector between the two Gaussians because it's a supervised setting, and just thresholded, just kept the top 200 features. Okay, so it's a very stupid approach, but this is what you get. Okay, so this is without sparsity, with sparsity, huge gains. And if I will zoom in into the bottom left part of the figure, you can also prove it theoretically that instead of P labels, you only need roughly K log P to be close to the base error. Okay, so if P is very large, this is a huge gain. But still, in this specific example, with 50,000 features, you still need something of the order of, let's say, 2,000 labeled samples, and you might not always have this number of labeled samples. So As we all know, feature selection is crucial in high dimensions. And the problem that I'm going to talk for the rest of my talk today is exactly semi-supervised learning for a sparse mixture of two Gaussians. So the setting we looked at was one in which we have a mixture of two Gaussians. The separation delta mu is k-sparse. I'll denote by S the support set. So this is a subset of P. And lambda, again, is the separation. I'm going to assume that lambda is 1. Okay, again, I'm going to take a sequence model as P and N tend to infinity. Also, K will tend to infinity. We'll see in a moment there are specific natural scalings for this problem. But I'm going to assume that the clusters don't get more and more separated. If lambda tends to infinity, then the problem becomes very easy, if you wish. Okay. And again, the goal is to construct an accurate classifier combining both the labeled and the unlabeled data. And so as an intermediate task, let's look at recovery of the support of the relevant features, okay? And the key question is, can we get a more accurate feature selection in a semi-supervised learning setting, okay? Does unlabeled data help us get much better classification? So for that, I want to first review briefly known results in supervised learning of a mixture of sparse Gaussians, then unsupervised clustering of a mixture of sparse Gaussians, and then we'll combine and see something hopefully interesting. So I'll start from the supervised setting. So the natural scaling for K is to be proportional to P to the alpha, and alpha is smaller than 1. So okay, so we have sparsity. And the natural scaling for the number of labeled samples is that it scales like K log P, which is where we can find the support, but then times some parameter beta, okay? And both Inkster and Donoho and Jean, they found that asymptotically there is a phase transition in the ability to do support recovery. If beta is larger than 1 minus alpha, remember alpha is the sparsity, then support recovery is easy. You just threshold the sample difference between the two, the empirical mean between the two Gaussians, and you get it. And if beta is smaller than 1 minus alpha, then it's impossible, okay? So this is what we know if we were purely in a supervised learning setting, okay? With enough labeled data, we can easily cluster, we can easily build an accurate classifier, and if we don't have enough samples, it doesn't mean it's impossible on an information theoretic perspective. Okay, let's move on to the other setting of purely unsupervised. So this would be clustering. There was a nice paper by Verzelen and Arias Castro, who also won a medallion award in this JSM. They proved that if the number of unlabeled samples is smaller than some K log P, then you cannot recover the support, no matter even if you have a supercomputer. And in contrast, if it's larger than some constant time K log P, you can recover the support with some, let's say, exponential time algorithms, let's say those that go over all possible subsets. And there are several works that proved that, and I'll go into this in more detail in a few minutes, but there were several papers that proved that if sample size is much smaller than K squared, then recovering the support seems to be computationally hard. We don't know of polynomial time algorithms that are able to do so. Now, in a paper with Robbie Krautgammer and Dan Vilenchik, and also proved by Deshpande and Montanari, we proposed some covariant thresholding algorithm, and if sample size is larger than K squared, constant, then there is a simple polynomial time algorithm that can recover the support. So here we have 3 regions in terms of the number of unlabeled samples. Too few a number of unlabeled samples, impossible to cluster. A lot of them very easy, very simple polynomial time algorithm. And in the middle, in principle possible, but seems to be computationally hard. We don't know of any polynomial time algorithm that succeeds in the middle region. Let me give you an illustration of the situation. So here I'm doing a 2D phase plane of the hardness of learning a mixture of two Gaussians. So the x-axis is how many unlabeled data you have. The y-axis is the number of labeled data that you have. And there are different regions. If you have enough, and of course, so any point on the x or y-axis is purely unsupervised or supervised, and any point inside the square is semi-supervised, okay? So let's see. So the rectangle at the top, it's a region where it's easy. You can just use the labeled data, forget about the unlabeled data, and find the support and construct an accurate classifier. The region to the very far right, it's easy because you can just find the support using an unsupervised method, using covariant thresholding and PCA. The region in red is impossible from an information theoretic point of view. And the question is what happens in the white region in between. It's a region where you have some labeled data, some unlabeled data, but not enough labeled data to be able to do something useful with it. And the unlabeled data itself, we could use it, but we don't know how to do it in polynomial time, okay? Okay, so you could also ask, are there regions in this square white rectangle, in this square where it's computationally hard, or are there regions where we can easily construct an accurate classifier in a semi-supervised learning setting? Okay, so a few years ago, Sam Hopkins, in his PhD, proposed, in terms of computational hardness, he tried to quantify when a problem would be, a hypothesis testing problem would be computationally hard. He proposed something called the low degree likelihood method. So suppose you have two distributions, P and Q. Q is going to be your null. P is some alternative. You can have many alternatives. And he proposed to see how well can we distinguish these two distributions, but not by any method, not, let's say, by the likelihood ratio, but only using low-degree polynomials. The idea is that low-degree polynomials we can compute in polynomial time, so if we cannot, so his conjecture was that, so he looked at this heuristic measure, and his conjecture was that if the distributions are nice, and this ratio remains bounded, it means that we cannot distinguish the two distributions by any low-degree polynomial. His conjecture was that this would be a hardness result. His conjecture was that this would imply that there would be no polynomial time algorithm that can distinguish between these two distributions. There was a lot of work applying this approach to various problems, finding phase transitions in terms of hardness, regions where at least polynomials, low-degree polynomials cannot distinguish, regions where they can distinguish, and we have methods indeed that solve various problems, sparse PCA, hidden click, etc. So we also use this machinery. Before I continue, I should say that, so first of all, there's a paper by, a recent paper by Alex Wine, which describes this framework, its history, various examples. The conjecture that Hopkins made, unfortunately, I don't know, or was recently refuted. They found some settings where you cannot distinguish certain distributions by low-degree polynomials, but you can still do some other polynomial time algorithm that can distinguish them. So this is the disclaimer. If we knew if P equals NP, then we could do other stuff, but we don't. I'm going to rely on this framework of low-degree likelihood. I'm going to look at, in a semi-supervised learning setting, other cases, regions where I cannot detect the support by a low-degree polynomial. Okay, this would hopefully be a proxy for the hardness of the problem. So in the work with Eyal Azar, we had two different contributions. One, we adapted this framework of low-degree polynomials, likelihood ratio, to our semi-supervised learning scenario, okay? We found a region where SSL would still be computationally hard or under this framework. And our second okay, that's the first contribution. Here's a kind of an informal statement. You don't need to parse it because I have a figure that explains it. It essentially says a very simple message. In the purely unsupervised learning case, there is a region where we could detect the support, but we just don't know how to do it in polynomial time. Now I'll give you a few labeled points. Intuitively, if I give you too few labeled points, it will still be hard. This is exactly what the theorem tells you, and this is its a graphical illustration. There is a region where even if I give you a certain amount of labeled data, it still doesn't help you, at least in terms of methods to detect the support using low-degree polynomials, okay? That's the interpretation of this result. So the question is, nonetheless, in the remaining white region, is there some other method with polynomial runtime that can detect the support and then construct an accurate classifier? And so our second contribution is we developed a very simple semi-supervised learning algorithm that can recover the support combining both the labeled and the unlabeled data. And here's where I combine the first part of the talk. So remember, the covariance matrix was rank 1, a spiked model. Its leading eigenvector was a separation. If we assume sparsity, then perhaps, so first of all, if we had enough unlabeled data, we could, of course, compute or estimate delta mu by vanilla PCA. If we don't have enough unlabeled data, this procedure fails. However, if we somehow were able to decrease the dimension, then we would have a better ratio P over N, and maybe then the separation would suffice. So the idea is very simple. Let's use the label data to do some variable screening, decrease the dimension, and then apply a vanilla PCA. Okay, so here's our algorithm. We compute the empirical mean of the positive samples, the empirical mean of the negative samples, compute their difference. This is this vector WL, the difference between the estimated mean of the positive and of the negative cluster. And you know, in variable selection, we would try to find which coordinates of WL, which is p-dimensional, contain the signal. Okay, but we don't have enough labeled samples, so I'm going to flip the idea around. I just can try to find at least a large set of variables in this high-dimensional vector that are just pure noise. Okay, so I'm going to, for some screening parameter beta tilde, I'm just going to retain the top p to the power 1 minus beta tilde entries of WL and throw away all the other ones. So hopefully I'll retain most. I'm not able to identify individually which coordinates contain signal or not. I just want to throw away a lot of coordinates that hopefully the vast majority of them are noise, and retain a sufficiently small subset of coordinates which at least some of them still have the signal. Okay, that's the main idea. And after I did that, so I did a dimension reduction, I'll just apply vanilla PCA, compute the sample covariance on this subset SL that I found, that I constructed, take the leading eigenvector, and maybe threshold it to the k largest coordinates, and this is my estimate of the support S. Once I have the estimate of the support S, I can apply LDA in low dimension, construct a classifier. Okay. So this is a very simple algorithm. It's you do thresholding, and then you do vanilla PCA. Okay. And we were able to prove that it actually works in part of this region. Don't read all the math. It's an informal statement. I have a picture that explains it. Let me. So the theorem says that in this triangular region, this method works. Asymptotically, it will give you the base error. Okay, this method has polynomial time runtime, computing the leading eigenvector of a sample covariance matrix, which has small dimensions. So, and now, let me discuss a little bit how you prove it, or maybe let me relate it to some work of other people. So first of all, this idea of throwing away coordinates that probably contain noise is somewhat related. I mean, we developed it for this problem independently, but in retrospect, it's quite related to the Sure independent screening paper by LV and Fan from 15 years ago. They did it in a regression setting. We're doing it here in a classification setting. The other idea why this works is that once we remove the dimension, vanilla PCA will just work. We know this from the phase transition of PCA. And then, of course, thresholding the eigenvector will recover most of its support, and etc. Now, in practice, after we remove the dimension, instead of vanilla PCA, we can apply any sparse PCA method that still has polynomial runtime. That will give you, in practice, better performance. Okay, so let me illustrate this result by some simulation. Okay, before that, let me just again clarify. In this blue region, it's a region where using the labeled data, you just couldn't construct an accurate classifier. Using the unlabeled data itself, we don't know any polynomial method that would be able to cluster the data. But if you combine these two sources of information, you can succeed. Very simple algorithm with the polynomial runtime. So it's a very interesting, in my view at least, phenomena. Okay, so let me illustrate it with a simulation. Here we took 100,000 samples, dimensions, sorry, sparsity of 100. For simplicity, I'm assuming the sparsity is known. You can adapt the algorithm to an unknown sparsity. Two Gaussians separated by lambda equals 3. And we look at two accuracy measures. One is how well can we recover the support, and the other one is what is the classification error of the corresponding LDA type predictor. Now we compared several methods. First, supervised, just take the top k entries of the empirical difference between the two Gaussians. Unsupervised, we applied the sparse PCA method we developed with Ian. We applied a method called IPU. It's a method to do sparse PCA, which works somewhat better. And for semi-supervised learning, I'm going to show you results with the scheme that I proposed here. But also, there is something very nice. It's called self-learning. It's used widely in machine learning. In self-learning, you first use your label data. You learn some initial classifier. You use it to construct pseudo-labels, predicted labels on your unlabeled data. You augment it and retrain. Okay, so it's called self-learning. So there is a sparse self-learning version in this paper, so we applied it as well. Okay, so here I had 200 labeled samples, and I start to collect unlabeled data. Again, the okay, so the horizontal line is what you get by just using the labeled data. The left is support recovery, so we only are able to recover roughly 20% of the support, and therefore the classification error is quite high. It's very far from the base error. If you try to do unsupervised sparse PCA, doesn't really work. You need many, many more unlabeled data for sparse PCA methods to succeed. This is what you get from the self-training. So because you're able to recover some of the support, your pseudo-labels are somewhat accurate, and you're able to pick up additional support, and you get better support recovery slightly, and hence smaller error. And this is what the performance that you can get if you apply our labeled screening PCA, or if you apply it with a sparse PCA procedure. You can, let's say, if you had 200 labeled samples and 2,000 unlabeled ones, you can get almost perfect support recovery, and then your error is very, very close to the base error. Okay, so by combining labeled and unlabeled data, you can get very close to the base error, whereas by methods that use each data on itself, we're unable to do so. Here I do a simulation where I keep the number of unlabeled data fixed and start to increase the number of labeled points. And again, the same picture. Using this label screening method, you can get very close to the base error with only very few labeled points. Okay, so this, I think, opens the way to many other questions, trying to understand what is the advantage of combining labeled and unlabeled data. So semi-supervised learning in other more complicated settings, like a mixture of multiple Gaussians, maybe for learning sparse representations. And there's also, like, maybe a more practical question is, are there realistic settings where semi-supervised learning improves over each of them separately, not only computationally, but also information theoretically, if you wish, okay? Okay, so I'll conclude my talk here. I think many of you know this. High-dimensional data brings many, many challenges, fascinating, at least for me, statistical, computational, mathematical problems. Semi-supervised learning, I think, is a not sufficiently explored setting, so I think it has interesting features yet to be explored. I described a case where you have high dimension sparsity, and by combining them, you can get substantial gains, at least on the computational side. Again, as I outlined, there are many, many open questions, and I'll end my talk here.
So thank you, Boaz, for a comprehensive and fascinating talk. So I have a microphone here. If you have a question and you would like me to bring the microphone, please wave, but the floor is open for questions.
Hi, Boaz. Great talk. So the majority of your presentation focus on eigenvectors and eigenvalues on the P by P feature matrix. Is that correct?
For the second part, what we did was use the label data to do dimension reduction, but then apply PCA on the remaining features, yes.
Yes. So my question is, have you thought about working on algorithms focusing on the n by n, people by people, like a sample by sample covariance matrix in your data? Because if you, for example, if your goal is to find the two clusters, then the eigenvector along the n by n, sample by sample matrix will give you sufficient information, because you kind of flip the problem since you have many features, and then that gives you good accuracy in terms of estimating the smaller n by n covariance matrices.
Yeah, I didn't go in that direction, but the phase transition tells you that you will not be able to detect the structure either if you look at the P by P covariance on the features, or if you look at the n by n covariance of the samples.
Yeah, I guess maybe the setting is slightly different, but in my work, I had experience dealing with the n by n, people by people covariance matrices, and I was able to prove the structure, at least the clusters can be recovered partially, and then you can actually use the n by n, people by people covariance matrix and the top eigenvectors, at least when learning the mixture of two sub-Gaussian distributions.
Okay.
Yeah,
so I'll be glad to discuss this offline.
Maybe we can bring offline. Thank you. Thank you. Yeah.
Well, I have to say, of course, I enjoyed the talk greatly. There's a kind of result that I learned about a while ago, which doesn't quite fit into this class. It's in a different setting, but I wonder if there is anything analogous. And this is a result by Spielman and Teng, I believe, on the behavior of the simplex method, which is known not to be, there are examples where it's not polynomial, right? But for perturbations of that bad situation, right? In fact, it works. I mean, there are known polynomial time methods, this interior method, but the simplex method, which is the most popular method, doesn't do it. I mean, I haven't seen any result like that in the statistical context, but I think it's sort of interesting. I mean, I'm not sure how you translate it.
Yeah, so I don't see a direct connection. The only thing I can think of is that in some cases, if you have data and your landscape of optimization is very rugged, sometimes if you add noise to it, you essentially smooth those very small local minima, and so adding noise may help you. But I don't see a relation to my specific.
No. I didn't think. Well, just in the scope of problems where you have this contrast of methods can do very badly, and this is also, of course, a high-dimensional phenomenon. As you let the size of the problem increase.
I wonder if you could go back to the phase diagram, the last one you showed.
Oops. Yes, so let me mention that in this phase diagram, first of all, we know that our method below the diagonal blue line, yes, will not work. And
when you say your method, you mean?
The label screening PCA. This diagonal line is where it stops working.
And my question there was, you showed the vanilla PCA and then you showed various sparse PCAs. Does this line apply to all of them?
Asymptotically, vanilla PCA, doing dimension reduction followed by vanilla PCA will be base consistent in that blue region. With finite number of samples, sparse PCA methods work somewhat better. But maybe I'll answer a question that I didn't ask. In the white region remaining, we don't know what happens. We have a conjecture that it's hard, or at least hard in the sense of no polynomial, low-degree polynomial method can work, but we were not able to prove it. So if there are young people in the audience that want to tackle a challenging problem and prove something in this white region, it's an open question.
Second part of the question, in the part that you have labeled hard, that was on the basis of the bounded degree issue.
Yeah.
Does that, is there something that, an algorithm that is hard that has been exhibited, or is this a lower bound statement?
Can you repeat?
Well, is there an algorithm that has been exhibited that might be very computationally complex?
Yeah, you can do exhaustive search over all subsets.
I see. So
that would work.
So there's certainly
yes,
an algorithm.
Yeah, it's possible but hard.
Okay.
Or we don't know of it's possible, we don't know of a polynomial time algorithm that would succeed.
Okay, thanks.
Hey, that was really interesting. I'm a more applied person than theoretical. And I had a question about your finding structure where there wasn't any. I assume you may know that one of the things that people do with omics data, so in some sense that's labeled. You have an outcome and you have a big vector matrix of features. But then people think, well, there might be batch effects. And so then they start looking in the matrix of features to see if there's some kind of separation. And from what you're saying, it looks like they'll find, you know, like a batch variable. It looks like it separates. But that's only really a problem if that vector turns out to be correlated with the actual original outcome, right? Because they're going to put it into a regression model, and they're going to adjust for it. So are you say you're guaranteed to be able to find some structure. Is it also true that you would be able to find structure that was correlated with a specific vector, like your outcome vector?
If I have high-dimensional data that does have some structure that is strong enough, then I will find it.
No, I'm saying if there's no structure, if there actually is no batch effect, but you run an algorithm, look for it, you discover, hey, I've got 2 gamma clusters, whatever. That's
Yes.
not a problem unless it turns out that direction is correlated with the true outcome.
So what I didn't tell you about this part is that there are many orthogonal projections that will all give you 2 clusters in that example.
Yeah.
Okay, so it's not a unique, it's not like there's only one, there are many. So,
But can you guarantee that?
no, so maybe one of them will be correlated with what you want, but many others will not be.
Okay, so you say maybe there's no result that you know of that says that you will always be able to find one that actually is correlated. With
Definitely not. How do you, putting computational issues aside, you can find many different pairs of projections that seem to reveal 2 clusters, let's say. You don't know which one of them is true and which is fake.
Right, but it doesn't matter which was true or fake unless it happens to be correlated with your outcome. Because I can find all kinds of directions, I'll put them in my regression, they won't matter. They're not correlated.
I see. Okay. I'll be glad to talk about this offline, but.
Really interesting stuff. I've got a more conceptual question. So in your talk, there were a number of asymptotic regimes. There was P proportional to N, there was P over N going to infinity, there was K proportional to P to the alpha, and some other things. How do you know which asymptotic regime? Is it determined by the problem you're solving, and you have to work out what it is? If you impose a regime, for example, it's very convenient in random matrix theory to have P over N going to a constant. You might get some result. How are you going to know that you're missing stuff?
So yes, the specific scaling is problem dependent. I should mention that although I did asymptotic results, you could also, at least for some of the things, you could, using concentration of measure, give non-asymptotic results that would hold with high probability. But yes, to study, to understand what is the correct scaling, it depends on the specific problem. Luckily, because I worked on semi-supervised setting where people have already worked on the supervised case itself and the unsupervised case itself, I knew what was the natural scaling to consider.
Okay.
Any further questions? If not, let's thank Boaz for a wonderful talk.